All right, well, so chapter 4, as you'll recall, is on aromatic compounds, meaning essentially benzene and compounds like benzene. For us, benzene is going to be kind of the archetypical aromatic compound. I think it's not going to be very common that we'll run into other aromatic compounds besides benzene. As I said, we will probably run into a couple in the chapter on heterocycles. We'll certainly see some of those heterocycles in the chapter, for instance, on nucleic acids, since we are doing biochem chapters as well. Something I might not have talked too much about, but I'm aware that this class isn't just organic chemistry. It's an introduction to both organic chemistry and biochemistry. I am no biochemist, but I understand the importance of at least going over the relevant classes of biological molecules, which you'll all have heard of from your high school biology classes. We're talking about nucleic acids, lipids, carbohydrates, proteins, things like this. At the very least, I want you all to come out of this class with a structural understanding, at least from an organic chemist perspective, of how those molecules are put together. And by the way, what I think you'll find, and I hope you'll at least be open-minded to, but and I think if you are open-minded, you will find that all of these molecules can easily be understood and explained by the material that we cover in this class. The same types of functional groups, same types of structural concerns, all those things will relate directly to the biomolecules. And that will then be, I think, helpful background if you go on to any other biology classes, anything that even touches on biochemistry, because there the structural treatment is exactly what you won't get. In this way, you'll have the background to be able to understand what they're talking about when you get to those classes. That's at least my goal. And so we are at the very least going to cover those 4 major classes of biomolecules. But that is, so, and there's a chapter on each one of them. So, you know, what does that make it? A quarter or a third of the course is related to biochemistry directly in that way. And aromatic compounds certainly do relate to those biological molecules. You'll find, for instance, when we get to proteins, polypeptides, amino acids, all those things, there are several of them that have aromatic rings on their side chains. So understanding how those work, how those are put together, you need to know something about aromatic compounds in order to understand what's going on with those. So I think even this chapter is helpful background. And so the way I would like to do this is to cover the reactions of aromatic compounds using strictly benzene as the starting material. That's what we'll start with. After that, we will consider what happens when there's already another group or multiple groups attached to the benzene ring, and we do these reactions. I'll just let, by the way, that area of electrophilic aromatic substitution is known as directing group effects. And I will just let you know right away, I am not going to ask you guys to be responsible for directing group effects. You may run into some questions on it in the OWL assignment. I will frequently do that. I will frequently leave some things, even things that I specifically say you're not responsible for. We'll go ahead and leave them in the OWL assignment so at least you're exposed to the ideas. But I'm not going to ask you to learn all the directing effects. But one thing I hope to convince you of by the end of class today is you don't have to know anything about directing effects to know something about how substituted benzenes behave. I think as long as I'm careful and thoughtful with how I phrase the questions, you certainly can still answer questions like that, even without knowing anything about directing effects. In other words, maybe another way of putting it is, the part of directing effects that's the most time-consuming to learn, which is the part I'm not going to ask you to learn, I don't think you even really need to know that in order to be able to handle the ideas. And so we can just skip all the time-consuming parts like that and get into kind of the essence of the matter, if you will, and you'll still be able to handle it. That's at least what I hope to convince you of by the end of the class. If we still have time left over, I can make up a couple problems for you to solve. If we still have time left over, it's Friday. We'll go home early, but that's kind of what I planned to do. So, or I mean, I can give a 2-minute introduction to chapter 5 without even writing anything, just waving my arms around like I always do, and then we can go home early. That's kind of like my plan for today. Good. So one thing I'm hoping you all remember, oh, that's better. I can see more of you now. One thing I'm hoping you all remember from chapter 3 is the reactions of alkenes with electrophiles. That's what we talked about in chapter 3. And we've already defined electrophiles as being Lewis acids. It's again another one of those strange things. This pair of terms, Lewis acid and Lewis base, and then you have this other pair of terms, electrophile and nucleophile. And honestly, as I stand here, I couldn't give you any meaningful difference between those two pairs of terms. An electrophile is a Lewis acid and a nucleophile is a Lewis base. I see no difference of any significance between those two pairs of terms. Why we have two pairs of terms, couldn't really tell you. But that's just another one of those things. It seems organic chemists just love it whenever you can have at least two terms for any one given thing. It's something I've especially started to notice as I've come here to Texas A&M. I don't know why it never occurred to me at my previous school, but I've especially noticed that in my time here, maybe as I've been able to focus more in my teaching. I'm like, why is that? Why do we have to have two words that mean the exact same thing? Well, okay, I'm not saying that we should never have any synonyms, but in a scientific field like organic chemistry, why is that necessary? Why do we have to have all these synonyms? Oh, well, it is what it is and we're stuck with it. In any case, what we learned in, I hit a button that I probably shouldn't have, maybe that, yeah, there we go. What we learned is that alkenes will react with any of a variety of electrophiles, or if you will, with Lewis acids, and they will undergo addition reactions of this type. And we talked about, I think at least 4 different addition reactions of alkenes. We did halogenation, we did addition of acids, we did hydration, and we also did hydrogenation. We almost want to put an asterisk there. Is hydrogen really an electrophile? Well, maybe. Maybe it is, you know. Hydrogen's kind of an interesting case, but be that as it may, it might still belong there. Whichever one of those 4, though, they all fall into this class, and these are all addition reactions. Remember, we defined addition reactions as being of the type A plus B yields AB. You have 2 or more molecules coming together to make one big one. That's an addition reaction. Aromatic compounds, or arenes, if you want to call them that, there you go again with the synonyms. Aromatic compounds do not undergo addition reactions with electrophiles. Instead, they undergo substitution reactions with electrophiles. And all their reactions are of this type, in which you have an electrophile switching places with one of the hydrogens in the aromatic ring, and you get a substituted benzene of this type. And you also do, I'm putting parentheses here, if you want to be picky about it, that's a terrible parenthesis, but I think you can at least see what I mean. If you want to be picky about it and actually balance the equation, there's not always, but at least oftentimes some kind of inorganic side product. This could be like HCl or H2O or something like that. Some small inorganic molecule as well. Not always, but oftentimes that's the case. Yes. In case you didn't hear it, question is, don't you get rid of the double bond in the substitution reactions? Good question, answer is no. You don't get rid of the double bond in substitutions. You do in addition reactions, and we did. There's no double bond any longer. But it's a good question still. Just because the answer is no doesn't mean it's a good question. That's exactly the point. We don't get rid of any double bonds in substitution reactions. Instead, that question was so timely, it almost looks like I planted it, but I swear I didn't. We did not talk beforehand. What happens in a substitution reactions is 2 groups change places. And that's exactly what's happening here. Can you see we're exchanging the hydrogen in whatever this group E is? So that group winds up on the benzene ring. And again, oftentimes you end up with some sort of inorganic side product. So that's why I say the one-word answer to your question is no. We don't get rid of any double bonds, not in substitution reactions. So it's a different kind of reaction. It's not an addition. It's a substitution reaction. And so there's about half a dozen of these substitution reactions that we're going to learn, including, interestingly, a reaction that's in your textbook, but is not in the 227, 228 textbook. So you guys are special. And it's not a complicated one. I think you can handle it. I have no doubt about that, actually. But so we'll go over that's what I want to go over first, is those 6 reactions with just benzene as the starting material, just to avoid any complicating factors. And then we'll consider what if there is already a group on the benzene ring. In other words, what if we treat with those reagents a benzene ring a benzene that isn't just C6H6. There's a methyl group or a carboxylic acid group or something already present. And again, I don't care if you learn all of the directing group effects. The usual phrase I use, I don't consider that to be a good use of your time. But you don't need to in order to understand the concept. And that's what I hope to convince you of. Good. So first of all, I might as well mention these 6 types of reactions. The order we'll go in is, first of all, halogenation, electrophilic halogenation. I'll write all these down too. Electrophilic nitration, sulfonation, addition of ethylene. That's the special one. And it actually is a very important reaction industrially, because there's a lot of compounds we make by addition of ethylene, or rather, well, it's an addition to ethylene, but it's still a substitution reaction on the benzene ring. So it's kind of both reactions at once. And there's a lot of industrially important compounds that are made in large-scale plants every day using that type of reaction. And we'll also cover Friedel-Crafts alkylation and Friedel-Crafts acylation. They're just called alkylation and acylation in your book, but I'm probably not going to be able to help calling them Friedel-Crafts reactions, because they're named after the people that were first involved in developing these reactions. So those are the 6 reactions. And I think that will probably take us through, most of the rest of the time. And then we'll spend a little bit of time on substituted benzenes. And I hope to convince you the idea is not as scary as you might think. I think you guys can totally handle it. All right, so first let's do electrophilic aromatic halogenation. In electrophilic aromatic halogenation, we will treat benzene, since we're always going to start with unsubstituted benzene, at least for now. We're going to treat it with some elemental halogen. So that's my arrow. And that halogen can be either chlorine or bromine. We've seen this type of thing before. So you can use either Cl2 or Br2. As always, F2 is too reactive. It'll just tear the benzene apart and you'll get CF4 and tetrafluoroethylene and things like that. You certainly won't get a clean product out of it. And you also need a catalyst. Unlike with addition reactions to alkenes, you need a catalyst. And that catalyst is going to be of the type MX3. And so the M, the metal in this case, M is a metal. It has to be either aluminum or iron 3. So you essentially have 4 choices, either Cl2 and AlCl3, Cl2 and FeCl3, or you can use Br2 and AlBr3, or Br2 and FeBr3. Those are your 4 possibilities, since the halogen may be either chlorine or bromine, and the metal can be either aluminum or iron 3, the ferrate ion. And in the end, what you will get is the corresponding halobenzene. Corresponding meaning it is the same number of carbon atoms. And what we'll do is we'll just replace one of the hydrogens on the benzene ring with that halogen. It will be with a chlorine if we start with chlorine. It will be with a bromine if we start with bromine. And so the way you'll know what to put here is by what you're given. I'm just here giving it in a very general sense because I didn't want to write that out 4 times with all the 4 different possibilities. I think you see what I'm doing here. But you will get chlorobenzene if you use Cl2 and either aluminum chloride or iron 3 chloride. You will get bromobenzene if you use bromine and either aluminum bromide or iron 3 bromide. So that's pretty much it. You do also get, as a side product, maybe we can put it in parentheses, you will also get either hydrogen chloride or hydrogen bromide as an inorganic side product. I think I've said this before, but it bears repeating. You'll notice that we organic chemists are kind of sloppy about balancing equations, certainly a good deal sloppier than they wanted you to be when you took Gen Chem. And that's because we care so much more about the organic product that we really care a good deal less about the inorganic side products. Those are going to be removed anyway when we isolate the organic product, which is again what we really care about. So in other words, halogenation of benzene will give you either chlorobenzene or bromobenzene, depending on the reagents you pick. And that's basically it. That's one of the 6 reactions. They're all about like that. Questions so far? Is that making sense? Well, next we will do nitration. In nitration of benzene, we'll again start with benzene. And the 2 reagents that we'll need in this case, or the main reagent we'll need, is nitric acid, HNO3, and sulfuric acid acts as our catalyst. And so what we wind up getting out of this is, I'll draw it 2 ways. You get nitrobenzene, it's a bizarre structure, but that's the nitro group. And you can also write it as, you can abbreviate that as NO2, that's allowed. So the nitro group is actually resonance stabilized. I could just as easily have made the double bond O over here and the single bond to oxygen over here with the minus charge on oxygen here. So the overall charge on the nitro group is 0. Overall, it's electrically neutral because you've got a plus charge on nitrogen in either case and a minus charge on oxygen. Oh, also a reminder, you may be wondering, why don't I just make another double bond to oxygen? Remember, nitrogen can't have more than 8 electrons around it, right? Your elements in the second row of the periodic table can never, ever expand the octet. Never, ever can have more than 8 electrons around it. So that's the reason why, because it otherwise looks like you could. Now, I will say if that were phosphorus, which is right below nitrogen, then you could. And I think that group also exists. But not with nitrogen. Never, ever. You can't ever expand the octet with nitrogen. So, right. So this is also abbreviated NO2. I don't care if you actually use that abbreviation. OWL might or might not care, so read the directions carefully. All I ask is that when you see that abbreviation NO2, you understand it. You understand it refers to the nitro group. And that's basically how the reaction works. I'm trying to see, I guess in a net sense, you will, gee, you know what? I'm not sure we can really say that. I mean, I know sulfuric acid acts as a catalyst. It certainly speeds up the reaction. But I guess one equivalent of sulfuric acid actually gets consumed because you will also get a molecule of water. You'll notice that we lose OH from the nitric acid, which in fact you do. We're not going to go over the mechanism, but if we were going over the mechanism, you'll see we do lose OH, and that needs to become water. So that's going to react, the OH minus is going to react with sulfuric acid to make water and the bisulfate ion, HSO4 minus. So, yeah, I guess we really should, if you're curious about the inorganic side products, they're water and the bisulfate ion, HSO4 minus. Might as well also remind you about the structure of nitric acid and sulfuric acid. HNO3 has this structure. I'm going to use my lone pairs because you've got some interesting charges on things. So that's the structure of HNO3, that's nitric acid. And I'll remind you about the structure of sulfuric acid also, H2SO4. And in fact, there you go. Here's a case where the sulfur atom is hypervalent. I think there's 12 electrons around sulfur, 2, 4, 6, 8, 10, 12. Yep, so that's allowed. With sulfur, you can do that. Oxygen, never. But with sulfur, you can do that. You don't have to. There certainly exist lots of compounds where sulfur is in the -2 oxidation state and behaves like oxygen. We've talked about thiols and sulfides and things like that. One of the things, by the way, when sulfur is in that fully reduced state and is an oxidation number of -2, always smells bad. And I know you've all smelled skunks and things like that, so that they have thiols and sulfides in their spray. So I just thought I'd remind you of the structure of nitric acid and sulfuric acid, respectively. Those are they. Good. Questions on either of those two reactions? Bottom line here is you treat benzene with nitric acid and sulfuric acid, you get nitrobenzene. So that's another one of our 6 reactions. You know what? I remember hitting record. I just want to check. Yep, looks like we're good. So you'll be able to, as I always say, stop that in the YouTube video if you need to, but unfortunately I need more space to fit the remaining 4 reactions on. After that, let's talk about sulfonation. And in sulfonation, we will take benzene. For now, we're always starting with just benzene. And we'll treat it with SO3. I should show you the structure of that as well. It's a little bizarre. And sulfuric acid, again, is our catalyst. And in the end, we will get benzene sulfonic acid, which has this structure. And actually, I don't think there's an inorganic side product here. We wind up taking a proton from sulfuric acid, so we'll get a bisulfate ion out of this. This can also be abbreviated. You can abbreviate that group SO3H. That's just a way of abbreviating it. You don't have to write it that way. If you'd rather write the group out, that's fine. All I ask is that when you see SO3H, you understand what they're talking about. They mean a sulfonic acid group. And might as well draw SO3. I actually remember getting in arguments with my physical chemist colleagues about this way back at my previous school when I used to teach Gen Chem. But I think the best way of writing SO3 is something like this. And now I'm trying to remember, is there a lone pair on sulfur? I guess there is. Now that I think about it, I think there is a lone pair on sulfur. And of course, that's again a resonance stabilized species. I could just as easily have made either of those other 2 oxygens with a single bond and a minus charge. So, but that I think is the best way. At least my understanding is you really don't want to write that with 3 double bonds. I don't think that fits our current understanding of the structure of SO3. But SO3 will undergo, that is, the SO3 will undergo addition. That gets added to, but the benzene ring still undergoes a substitution reaction. And actually, you can see, now that I think about it, we are even on protons. I don't owe you a proton, and you don't owe me a proton, because we substituted one of the hydrogens on the benzene ring. And so you see, we have a new hydrogen over here. Now, probably that's not going to be the same hydrogen that came from the benzene ring. It probably actually came from the sulfuric acid molecule. But in terms of a net sense, neither of us owes the other party any protons. So I think in this case, we're right to say that sulfuric acid is, oh, you know what? I hope I could do both Control Z and Control Y, because I realized I made a mistake. So we'll see if it works, because I want to get the previous page on here. Let's just see if I can do Control Y. Yep, that does work. I think my math sucks, to be honest. Let me see. Oh, I did make a mistake. It's not a major one, but I realized we don't get a bisulfate ion. It's the same thing over here. Might as well make the change in your notes. Actually, once again, with nitration, we are even on protons, because as you can see, HNO3 minus OH gives you the NO2 group, but we also replaced a hydrogen on the benzene ring. And if you want to think of it as H and OH make water, then we're fine. But actually, see, that's what I thought, is that sulfuric acid is a catalyst for that reaction. Oh, gee, wait, that might have just ruined everything. Crap, it did. All right, well, I'll rewrite that. Sulfonation. It should be benzene, reacts with SO3 and sulfuric acid. I'll redraw SO3 again also in case anyone needs it. And the exclusive product here is benzene sulfonic acid. There's no inorganic side product. And to remind you about how SO3 looks, there's a plus charge in sulfur and also a lone pair on sulfur. And of course, we have these lone pairs on oxygen. Good. Yes, I like that. So in both cases, sulfuric acid is a catalyst. There's no sulfuric acid consumed over the course of the process. That's what I thought. So yet again, I was rushing when I made my lecture notes that I'm reading off of. And what I have here is incorrect. I need to remember to fix it. What's over here now is correct. So please make that correction in your notes as well. Good. I feel better about that. I may be the only one who feels better about that, but I feel better about that. Good. So much for halogenation, nitration, and sulfonation. Let's move on to the next one, ethylene addition. Ethylene addition is actually kind of like sulfonation in a way. I'll explain. But in ethylene addition, we will take benzene and ethylene. Ethylene is the simplest possible alkene. You could, in principle, call it ethene, but no one does. People call that ethylene. Oh, I already wrote it up there. Ethylene. And once again, sulfuric acid is going to be our catalyst, and we will get, as a result, ethylbenzene. And there is no other inorganic side product. So this is actually interesting because ethylene is an alkene, and we understand that ethylene undergoes addition reactions, and the ethylene does undergo addition. We've essentially added benzene across the alkene. So that's kind of intriguing. But the aromatic ring does not undergo addition. The aromatic ring still undergoes substitution. We replace a hydrogen with that ethylene group. And you can see that once again, we are even in terms of hydrogens. We did go from CH2CH2 to CH2CH3. So there's an extra hydrogen here, but we also took a hydrogen off the benzene ring. So we are again even in terms of mass. And I would say once again, sulfuric acid is a catalyst. It's neither consumed nor further generated. It's simply regenerated and takes the same form at the end as at the beginning of the reaction, which is exactly how we define a catalyst. So that's I'm kind of excited about that, because the reason I look a little excited about this is because so far our catalyst is, at least for these reactions, is always sulfuric acid. I guess the catalyst for the other previous two is an aluminum or iron 3 halide. And I think for our last two, it's going to be the same iron 3 or aluminum halide. So that means there's only two different catalysts. For some of these, sulfuric acid is the catalyst. For some of them, the metal halide is the catalyst. And in both cases, we really do mean a catalyst. It's neither generated nor consumed over the course of the reaction. At the end of the reaction, it is the same form as it had at the beginning of the reaction. Good, so that's ethylene addition. That just leaves us with our two Friedel-Crafts reactions. The first one is alkylation. And in a Friedel-Crafts alkylation reaction, we start with benzene, and we're going to add some alkyl halide, and R can be pretty much anything. Any alkyl group, at least. And our catalyst, once again, is going to be either the aluminum halide or the iron 3 halide. So aluminum or iron 3. And in the end, you will get the alkyl substituted benzene. That alkyl group, whatever it might be, will replace one of the hydrogens on the benzene. And you do indeed, in this case, get an inorganic side product. You get the hydrogen halide. So as an example, let's say we took benzene and we treated it with bromomethane in the presence of aluminum bromide as a catalyst. I would expect that we would get toluene. And of course, plus HBr. We don't even always write the inorganic side product, but that would be one example. We'll do one more example. Let's say we treated benzene with tert-butyl chloride. So 1, 2, 3, 4 carbons. And let's say we used iron 3 chloride, FeCl3 is the catalyst. In the end, I would expect we would get tert-butyl benzene. Plus, of course, HCl. So those are two examples of Friedel-Crafts alkylations. As you can see, whatever the alkyl group is that you're given, that simply takes the place of a hydrogen on the benzene ring. The reaction, by way of full disclosure, isn't terribly general, but that's not your problem. That's my problem. That's just something I have to think about for any questions that I write, just to make sure that I'm telling the truth. That's not your problem. I don't think you'll need to worry about that. And I expect OWL will not do anything. Okay, OWL sometimes does crazy things, but I don't think they do flat false things. You know, they don't do things that are flat out untrue. So I don't think it's going to be an issue. Good, so that's Friedel-Crafts alkylation. Any questions on either of these reactions? Either ethylene addition, yes. Plus HCl. Let me write this out in another way. I'm just going to rewrite the reaction differently so you can see what that is. I just wrote it out with condensed structures. It's just another way of doing the same thing. Other questions? Well, Friedel-Crafts acylation looks, actually, I'll even put it up here, looks somewhat related to that. Before we understand what acylation is, we need to understand what an acyl group is. And an acyl group is defined, I'm going to define it with a picture, with a structure, rather than with words. But this is the definition of an acyl group, where R is any alkyl group. It means you have a carbonyl group with an alkyl group on one side, and the other side is attached to something else. And regardless of what that something else is, you've got yourself an acyl group. And in an acylation reaction, we will replace one of the hydrogens on benzene with an acyl group. That's basically how that works. So the general case of an acylation reaction involves taking an acid chloride, which is a functional group closely related to carboxylic acids. Again, it's pretty general. R can be pretty much anything here. And we again will need some chloride catalyst. I don't know that it really matters, but my instinct says we should match the halogen. Could this be a bromine instead of a chlorine? In principle, yes, but in real life, acid bromides are very rare and hard to get your hands on and pretty unstable. Acid chlorides, on the other hand, are very, very common. Thousands exist commercially, and you can easily get your hands on them. So I think in practice, you'll find this is always chlorine. But again, the metal can be either aluminum or iron 3. That part stays the same. Both aluminum and iron 3 are fine. And in the end, you will get a ketone where you've replaced one of the hydrogens on benzene with that acyl group. And as a side product, you once again will get HX. Oh, sorry, HCl actually, since X is going to be I think you'll find in practice the halogen's always chlorine in this case. So you do get that as an inorganic side product, but the major organic product will be a ketone, an aromatic ketone of that type. Let's do a couple examples of this type of reaction as well. Let's take benzene Ooh, I should be using colors for this. I keep forgetting I have colors. I feel so powerful. Let's say we used aluminum chloride as our catalyst. I would expect that you would get acetophenone, which is a compound that you know the name of, because we talked about that last time. Let's say instead that we treated benzene with benzoyl chloride. Oh, here we go. I can do pH for phenyl, since we've defined that. And let's say, just because I feel like it, let's say we used iron 3 chloride as our catalyst. Once again, you would get the ketone. In this case, the ketone you get would be something called benzophenone, which is 2 benzene rings. So one of the benzene rings comes from our reagent, the benzoyl chloride. The other one comes from the benzene that we started with. And so this is also a compound that exists. And I guess in both cases, you would get HCl as well as a side product. We don't always write that. Watch OWL carefully. I just want to give you a free word of advice. Watch OWL carefully. Sometimes they will want you to draw a separate sketcher and put the HCl in. You know, read the directions carefully. In fairness, they do generally tell you what they want you to do, but you have to read the directions carefully. Good, and that's it. Those are the 6 electrophilic aromatic substitution reactions. So those are fine as far as reacting just with benzene, just with unsubstituted benzene goes. What if there's already a group on the benzene ring? In other words, what if we don't start with benzene? What if we start with toluene or benzaldehyde or chlorobenzene or phenol? What if we start with one of those compounds that we talked about the other day? And the answer is the pre-existing group, the one that's already on the benzene ring, will effectively tell the new group where it needs to go. And there are rules that define that. And I think you would be completely capable of learning them. I just don't want to add any more as regards that to your burden than we already have. I think 6 reactions is enough. But that being said, what I hope to convince you of is that you don't need to know anything about that in order to answer questions. For example, you might run into a question like this on OWL or even on exam number 2. Let's say the question is something like this. What is the reagent that you will need in order to carry out the following transformation? Or something like that. Don't focus too much on the wording. Basically, the question is, what do we fill in the question mark with? What's the reagent that you need in order to carry out that transformation? And that's a question I think you can answer, even without knowing about directing effects. What you need to do is look and see what has changed. And I think you'll agree that we've replaced a hydrogen with a chlorine. Everything else is staying the same. The benzene ring stays the same, and the methyl group on the benzene ring stays the same. What we're doing is we're replacing a hydrogen with a chlorine. Well, I would put it to you, and you don't have to know it right now, but I think by the next exam you will know it. We know how to do that. The reagents that we need are chlorine and either aluminum chloride or iron 3 chloride. Either one of those would be acceptable. You could write FeCl3 also if you wanted to. And that will replace the hydrogen with the chlorine. That's a halogenation reaction, an electrophilic aromatic halogenation. Now, as it turns out, the methyl group is what we call para-directing, meaning that it directs the chlorine to go para. You don't know that, and you don't need to. I know that. You don't need to know that in order to answer that question. If the question is simply, what do you need to add to toluene to get 4-chlorotoluene? The answer is Cl2 and either AlCl3 or FeCl3. You can answer that question without knowing anything about directing effects. I'll do another one. Maybe I'll do two more like this. Let's say we started with benzoic acid. Ooh, I promised I wouldn't do that anymore. Let's say we started with benzoic acid and you wind up with metanitrobenzoic acid. What reagent do you need to carry that out? You can answer that question. You don't need to know anything about directing groups in order to answer that question. What you do is you look and see what has changed. Looks to me like we've replaced a hydrogen with a nitro group, NO2. Well, we know how to do that, at least in principle. That's an electrophilic aromatic nitration. And the reagents that we need are nitric acid with sulfuric acid catalyst. And that will carry out that transformation. Again, as it turns out, the carboxylic acid group is what we call metadirecting, meaning that the new nitro group will come in meta to the carboxylic acid. You don't need to know that. And it's okay that you don't know that. You can still answer that question, even without knowing. Again, I know it. Not to brag, it's not really a great feat in my part. By now, I'd better know that. But you don't need to know anything about that in order to answer that question. Let me show you another question, type of question that you can answer. And then maybe I'll let you out a couple minutes early because I think you're getting the idea. Let's say instead of filling in the reagent, you would to fill in the starting material. Let's say that we treated something, question mark, with sulfur trioxide and sulfuric acid. And in the end, we got what? What did we get? We got this. Oh, let's go crazy. Let's put a methyl group on there also. So you'll approach it the same way. How do we figure out what the starting material is? Well, first of all, what does this reagent do? That reagent replaces a hydrogen on a benzene ring with a sulfonic acid group. There's my sulfonic acid group. That must have gone on because of the SO3 and sulfuric acid. So it means that in the starting material, where we now have this sulfonic acid group, there used to be a hydrogen. And so that's what you'll draw. That's what you'll put for the starting material. You'll leave everything else the same. The OH in the methyl group will still be there, but now there's just a hydrogen here. You can draw the hydrogen if you like, draw bond H if you want to. You don't have to, it's understood. But what have I done down here? When you treat this compound with sulfur trioxide and sulfuric acid, you will get this sulfonic acid. And again, you don't need to know anything in fact about directing groups in order to know that, because you can see what changes taken place. Or if you're given the reagent, you know what the reagent does. This reagent replaces an H on benzene with a sulfonic acid group. There's my sulfonic acid group. That means what I started with had to have a hydrogen there. And you don't need to know a thing about directing effects. And trust me, it's one of those things that would be a ton of work for very little benefit. And it's another one of those things that I just judge it not to be worth spending your time on. So you're not responsible for directing group effects. I was pretty clear in the class notes which parts you're not going to be responsible for. I think I'm pretty clear in the syllabus as well. But my point is, you don't even need to know that, and you can still answer questions like this. So you'll have a chance to look at some of those in OWL. There may be some questions also where you'll have to read up in the book about directing effects just to answer the question. I don't mind you being exposed to those ideas. But again, in the class notes and in the syllabus, I think I'm pretty clear about what you do and do not have to know, and what you are and are not responsible for. And my point is, there's no need for you to go through all that work. You can already understand some of these things. And with that, that's 2:38. I call that close enough. I don't mind letting you go 2 minutes early on Friday. So have a great weekend. I will see you all on Monday. Check Canvas, I would say by Sunday night. I hope at least your raw scores will be available by then. Other than that, have a great weekend.